Assalamualaikum warahmatullahi wabarakatuh. May I have your attention, please? Good morning, ladies and gentlemen. I would like to welcome you to this seminar. Please let me introduce myself. My name is Diah Anur, and I will be the Master of Ceremony and also the moderator for this colloquium, which theme Microscale innovation in Microtechnology, Miniaturization, Microfabrication, Microsystem device of metal device. Currently, we have an exciting panel of 2 speakers for you today, and I hope that you will find their presentation and discussion informative and also engaging. So please enjoy the seminar. Before we begin, I would like to take a few moments to explain the rule for the seminar today. First, please make sure to mute your computer when you're not talking, and please open up the camera so it will be more attractive. So the speakers can see your face. And we also encourage you to participate in the discussion and ask questions related to the seminar. For every session, we will give the opportunity to ask the question at the end of the session. And you can use also the column chat to write your question, and don't forget to put your name and affiliation. And I hope you will adhere to these rules and participate in the seminar. Thank you for your cooperation. Without further ado, let's begin the seminar. Bismillahirrahmanirrahim. First, I would like to invite Ms. Ika Kartika as the Chief of Research Center for Metallurgy to give an opening speech. Ms. Ika Kartika, the time is yours.
Okay, thank you, Bu Dia. Assalamualaikum warahmatullahi wabarakatuh. Bapak Ibu, good morning. Thank you for attending our colloquium today. So our topic for today called Microscale innovation in Microtechnology, Miniaturization, Microfabrication, and metal device microsystem design. So Research Center for Metallurgy, National Research and Innovation Agency is currently developing a new design for an alloy for numerous medical devices such as clip aneurysm. So from clip aneurysm, we already collaborate with neurosurgeon specialist at Siloam Hospital in Karawaci, Tangerang. And for this collaboration, we have several patent design for clip aneurysm. And today we also want to talk about microtechnology, miniaturization, microfabrication. And here, this topic is very important for metallurgists, especially microfabrication techniques, because microfabrication techniques can correlate with advanced technology such as additive manufacturing, atau here is 3D printing and bioprinting to make implant and prosthetic devices. So Research Center for Metallurgy has 2 young researchers capable in biomedical engineering. Here we can clear the presentation from them. So I hope today's presentation will be beneficially for us. Thank you for taking the time to attending to our colloquium today. Thank you very much. Budia.
Thank you, Ms. Ika Kartika. Okay, before we begin the presentation, we will have a photo session first. Please open up your camera. And Ms. Rida, please help me to take the picture.
All right, let us start with the first slide. Second slide. Done. Back to Miss Dia.
Okay, thank you, Miss Rida. Okay, now we will continue to the first speaker, Pak Satrio Utomo. Before we start the presentation, I will read his bio first. Actually, he will talk about introduction to miniaturization, microfabrication, and microsystem. I have so many papers. Our current young researcher, Mr. Satrio Utomo, he has finished his bachelor degree in University of Indonesia, majoring in mechanical engineering, and he also completed his master degree in Wayne State University, USA, biomedical engineering, and currently he is a PhD candidate of University of Melbourne, majoring biomedical engineering. Started since 2023, and we hope he will finish his PhD degree soon. Okay, he also, besides as a researcher, he's also a lecturer in Department of Physiology and Biophysics, University of Indonesia, and he also published some scientific publication, some recent publication which title Effect of Flow Rate Modulation on Alginate Emulsification in Multistage Microfluidics, published in the Micro Machines in 2023. And he also published about from imaging data to cranioplasty implant design at 2023. Okay, to make it quick, I will give the time for Mr. Satrio to present his topic. Okay, Mr. Satrio, please.
Okay.
The time is yours.
Yep. Let me just share my screen for now. Okay, so I hope you can see my share screen right now. Okay, so Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, good morning. So I was asked to deliver the seminar today in English. I hope you all agree with such condition. My name is Satrio, and I'm currently working toward my PhD at the Department of Biomedical Engineering, University of Melbourne, Australia. And then thank you to Budia as the moderator. Thank you to the researcher and staff at the Research Center for Metallurgy for hosting this seminar. And thank you to all of you for attending the seminar. So for the next around 30 minutes, I will try to bring up discussion on introduction to miniaturization, specifically on microfabrication and microsystem. Okay. Yep. Okay, so I will start the discussion from a movie called Downsizing, which was released in 2017. So in this movie, a scientist successfully developed an irreversible method to downsizing or shrink materials, including human. So if you can see here in the picture on the right side, that you can see that there are large and there are the small humans. And this scientists introduced this technology to public. They got people attracted to the technology and successfully built this miniaturized world. What might be interesting from this movie, the reason why I take this movie as an opening for this seminar is that the argument behind this development of such technologies is to solve the overpopulations and environmental issues. And this might make sense in our current world, considering that if we can shrink human populations around the world, then our needs to resource can be reduced. And we should consider such way of thinking, because in our world today, the overpopulations, along with the consumerism, the natural greedy behavior of human, with limited resources to food, energy, and appropriate living space, has led issues to health, environmental, and socio-economical issues in around the world. And if we see the statistics here, at the end of around at the end of 2022, the human population is expected to reach around 8 billion people, and it is predicted that this number to keep growing more and more. And Indonesia is among the most populous nation in the world, just below the China, India, and USA. And I think all of us here have been experienced the actual effect of these issues due to the overpopulations, such as like for the last couple of months, we read and heard news about the worsening air quality, especially around the Jabodetabek area, and also pollutions in air, water, and soils, issue on waste, and then drought, and then increase of global temperature. For now, maybe for examples, like maybe a couple days ago, in Jabodetabek, the temperature can reach almost 40 degrees Celsius. And if we do not think about solutions to this problem, then there might be not be a good place for our descendants to live in the future. And for centuries, human has built their civilizations through several stages of industrializations. Now we are currently at the fourth stage of industrial revolutions, where we are faces with technological advancements such as robotics, artificial intelligence, machine learnings, Internet of Things, big data, 3D printing, and such. What we shouldn't forget about these stages of industrial revolutions is that each stage actually depends on the previous stages. Like the industry 4.0 will not exist if there is no era of electronics or automations during the industry 3.0. And the industry 3.0 will not exist if there is no era of electricity in the industry 2.0. And even until now, we still rely on the technology of internal combustion engines, steam turbines to generate powers, which is the product of the industry 1.0. And from the perspective of material technology, we can see that for around last half of century, our technological advancement are based on silicon-based or semiconductor materials. And now we are moving toward the era of micro or nano technology, nanomaterials, and even more lower dimensions, such as like two-dimensional materials. Okay, and so I would say that the foundational key element of our digitalized world today is this small parts called transistors, which we may consider as the brain cells of computers and electronics in general. And I think most of us have experienced in the first place how this technological advancement evolve. So maybe a lot of you have experienced how computers are getting more and more smaller, lighter, more compact, more powerful. And then it's not just about computers, but also cell phones. So maybe even back in my childhood, the cell phones are still considerably old compared to now. There is no touch screen. The screen is just monochromatic, black and white. But now the phones are just not to call and send text messages, but they can also do a lot of things. Even the computational power of smartphones today is more and more powerful than computers, which is like as large as a cardboard, like maybe 20 to 30 years ago. And this is due to this evolutionary process of these transistors. So for examples, like in 1941, the transistors is like as large as a light bulb, but due to this technological advancements of microfabrications, now we can have transistors as small as tip of your fingers, and this will lead to advancement in the electronics. And when we discuss about miniaturizations, we will arrive to this law by Gordon Moore, who is the one of the founder of the Intel, one of the largest semiconductors companies today, and can be considered also as the pioneer of this miniaturization technology. So basically, he predicted that in every 2 years, from the era of 1960s to 70s, the number of transistors in the same physical space of a circuit will be doubled, which means that the computational capacity of computers will get more and more stronger. In the image here on the right side, we can see how in a considerably same size of chip, the amount of transistors is getting more and more dense. It's now we can have like millions of transistors in just a small size of chips, and this is due to this microfabrications technology. Slide. Now, when we're talking about microfabrication and microsystems, we are talking about products at the scale of 100 microns to 100 nanometers. So above the scale, we can consider the process as a precision or conventional fabrication. So usually when we work on just a conventional fabrication process, we deal with some products that have level of details in millimeters or centimeter scales. But as we go down to micrometer scales, this is where we have this microfabrication technology. And then below this 100 nanometer scales, we have this nanotechnology when we deal with products in size of 0.1 to 100 nanometers. So this is the scales that we are talking about today. And in general, there are two ways to develop products. We have the top-down approach and we have the bottom-up approach. In this session, we will discuss how the microsystem can still be developed using the top-down approach. While this bottom-up approach is more on the nanotechnology side, such as synthesis of nanoparticles. But for now, we are talking about the microfabrications from the top-down approach. And there are 4 categories of microfabrications method that we will discuss here. For the first category can be considered as the miniaturizations of the conventional fabrications method, where we still use physical tools to shape the materials. The second group is when we use lights to shape the products. The third group is when we use chemicals or ions to develop the products, and the last group focus more on the deposition or the addition of materials in a nano or a micro scale. So I will start with the first method, the micro milling. So I think we'll know in general about milling process just in a conventional fabrications where we have tool heads rotating, and then we have workpiece, and then this workpiece and the tools will move in XYZ directions, so we can have products made from the workpiece cut by the tool head. But in micro milling, we can just consider that the tool head will be just as small as this size. It's approximately in 100 scale of micrometers. So if you see here that we have this match stick head, and then this is the size of the tool head of the micro millings, and what differs from micro millings to conventional milling process is that in conventional milling process we use an electronic motors to run the tool head, but in micro milling we use rotary pneumatic, so it's kind of like a small turbines to turn the tool head, and then the spindle speed. So we are talking about 100,000 of RPM. In conventional milling, we are talking about maybe 100 or thousands RPM, but in micro millings we're dealing with 100,000 of RPM. The depth of cut is also considerably shallow, should be lower than 500 microns, and the materials that we can work with micro milling is considerably soft metals like aluminum, copper, or maybe rigid polymers such as PMMA or acrylics. And the resolutions of micro millings can reach about 10 microns. Okay, so this is the first microfabrication method, micro millings, and then the next process is hot embossing. So I think we are so already familiar with this kind of fabrication process. Like in metalworking, we have this stamping process where we have hot metal plate, and then we use jig, we use dies to form the metal plates. In this kind of approach, we also use heat and pressure to form or transfer micro features to materials such as PMMA or acrylic or PDMS or polydimethyl siloxanes. And this kind of process is usually used for mass production of micro products. So on the right images here, we can imagine that basically it's just the same process with a conventional stamping process. We have a stamp here, we have the substrates or the polymers, and then we heat up the systems, and then we push the polymers with the stamp, and then we take off the stamp, and then we will then have this form substrates at the end of the process. And this is the examples of the actual mechanism. So we can, if it's done for mass fabrications, so we can consider a continuous process. So we can use this kind of rolling cylinder to form these plastic sheets. And this is the examples of a flexible micro fluidic chips that are formed using this hot embossing process. And we can consider the micro milling the previous process, the micro milling process, as the prototyping method to develop the stamp, and then we can then replicate or do mass production of the device using this hot embossing. So it's kind of a continuous way to develop a micro products. Okay, so we already talked about two methods that are based on conventional machining process, and then it's being miniaturized into a smaller process. But now we are talking about a different ways to develop products. In here, we have a soft photolithography where we use lights to help us to develop the products. So in photolithography, we have these two-dimensional ways to develop products. So we will have mask here that will contain our patterns, and then we will use a light source to induce chemical reactions to our photoresist here, and we will deposit the photoresist on this substrates, which is usually a silicon wafer, or it can be like another materials that we will discuss later. And the way we develop micro products from this photolithography is then we can use this master device from the photolithography to get this PDMS based microchip, and then we can then use this micro PDMS chip as the final product. Okay, so I will discuss more about this soft photolithography process, starting from the silicon wafer or the substrate materials for the common photolithography process. So the silicon wafer itself is usually fabricated using either of these two methods. If it's not this Koralski or the float zone methods, and in these methods, basically what we do is we melt the polycrystalline silicons into this furnace, and then we will put seeding crystals on top of the melt polycrystalline silicons, and then we will then do this rotating and pulling of this molten polycrystalline silicons, and then we will have this monocrystalline silicon ingots, which is will look like this, and then we will then cut these ingots into a disc or wafer like this, and this disc will come in a various size, starting from maybe 3 inches to 4, 5, 6, or maybe even larger size for mass productions. And the silicon wafer are usually not fully in a circular shape. Usually they will have like 1 or 2 sides that are blunt like this, and there are meanings of those sides, which is the crystalline directions of the silicon. So in here we have like a different crystalline directions of the silicons, and the way people differ each of the products is by having this small dent or sides that is blunt. Okay, so this is about the silicon wafer itself. And then we also have another substrates that we can use to do the soft photolithography process, which is this lithium niobate wafer, and they're usually used for piezoelectric applications. And the process would be almost same. We will have this kind of ingots, and then the ingots will be cut into this circular disc or wafer, and the piezoelectric, this lithium niobate wafer is usually transparent. And then the reason why these materials are special is because they have a very high electromechanical coupling coefficients, which means that by just using a very small amount of electric current, we can have these materials to vibrate or oscillating. And that's the reason why people use this substrate as the piezoelectric device. And I will explain more about the piezoelectric application of piezoelectric device in our daily lives. And this lithium niobate wafer also have a good chemical and mechanical stability. Okay, so the next materials that we usually use in soft photolithography process is this photoresist SU8 and also its developer. So this SU8 photoresist is a special chemical that can get cross-link or harden when it's exposed to UV lights. So it's something like this. It's kind of like a thick viscous liquids, and this is the developer. And the way we use these chemicals is at first we coat this SU8 on top of the silicon wafer using this kind of spin coater. So we put the silicon wafer on top of this spin coater, and then we put SU8 on top of the silicon wafer, and then we spin the silicon wafer to get kind of even thickness of SU8 film. And then we will do what we call a soft baking, or basically heating up the silicon wafer to get the SU8 stick to the silicon wafer. And before I continued about the soft baking process. So we usually have a lot of SU8 products, and they are defined with the how the film thickness would relate to the spinning speed during the spin coating. So say if I want to get a 50 microns thick film, I can try to spin an SU8 2050 at 3000 RPM to get a 50 microns film thickness. And then based on the thickness of the films, I should bake the SU8 on the silicon wafer for this temperatures and time. And then after I do the soft baking, I expose the SU8 using UV lights. So I put mask over the SU8, and then I expose the SU8 over the mask using this specific energy of UV lights. And then after that, I do this post-exposure baking based on the thickness of the SU8 films. And then after that, we develop the SU8 using this developer. So we just put the silicon wafer into this solutions, and then wait for some times, and then we can get the micro features, which we can see later on in these presentations. Okay, so another materials that we usually use to produce micro products is something what we call as PDMS, or polydimethyl siloxanes. It's kind of a flexible polymers. It's quite flexible, and it's a good materials to mimic biological tissues. It's biocompatible, it's chemically inert, it's gas permeable, so it's widely used in biological applications. It is optically transparent, so we can observe what's going on inside the device under the microscopes. And the way we use these chemicals or PDMS is we mix the PDMS elastomer and the curing agent, usually 10:1 ratio. So they usually comes like this. We have this elastomer, and this is the curing resins. So we mix them together to 10:1 ratio, and then we degas, or we take out the air from the mixtures, and then we will pour down the PDMS on top of the silicon wafer. There's already have micro features from the soft photolithography process. And then, so when we have the PDMS mixed with the curing resin, we can put them in a room temperature for like 48 hours or like 2 days, and then they will get solidified. But if we want to get them solidified faster, we can put the PDMS into an oven for like 80 degrees to 80 to 100 degrees Celsius for 2 to 4 hours, and then we can have this kind of solidified PDMS, and then we can cut and then peel the PDMS from the silicon wafer, and then we can bond the PDMS on this, for example, on the glass slide of this microscope slides, and then we can have this kind of working microfluidic device made from the PDMS. So another materials that we can use to get micro products is this rigid polymers. So we can basically use just PMMA or acrylics, something like this, using maybe laser engraving or using micromilling. We can get this kind of small channels, and then we can try to flow liquids into these channels, and we can try to bond acrylic chips using this kind of methods. So basically using acetones of gas, we expose the acrylic to acetone gas, and then we can bond them together. We also have polycarbonates and this COP or COC, the cyclic olefin copolymer. So a lot of commercial microfluidic products use this kind of rigid polymers as their materials, and the way industry mass produce the this kind of device is usually using this kind of just injection molding or the hot embossing process. So we can get the mold either using micro milling or soft photolithography, and then we can do this mass production using as simple as injection molding or hot embossing. Okay, now we are going deeper. So we will have something called multi-photon lithography. So in soft photolithography, we still use just an array of UV lights to form our microfeatures. In this multi-photon lithography, we use a laser. So we will have a more focused, a stronger light source to have our features. So for example, using this kind of technology, we can have features as small as this structure. So if you can see here at the tip of this pencil, people can develop this kind of castles, structures like this using this direct laser wiring or direct laser lithography, and using this kind of methods, we can also do what people call as two-photon polymerizations. So in two-photon polymerizations, we can use the SU8, so the materials that we already discussed previously. So we can put SU8 on top of substrates, and then we can have lasers coming up from the top and bottom side of this photoresist, and then we can have the SU8 crosslinks in a specific voxel or points inside this three-dimensional space. So we can have this kind of structures. If you can see here, the length scale is 10 microns, and using this kind of technology, we can have this scaffolds, an arrays of porous cubic structures in this kind of scales. We can have this kind of structures. If you see here, it's a porous cubes size 5 microns. It's about 450 microns high, or something like this, and we can have something like this using this two-photon polymerization method. So it's more detailed, more advanced method than the soft photolithography methods. Okay.
Kindly reminder, Mr. Satrio, only 5 until 10 minutes left.
Okay, 5 until 10 minutes. Okay, thank you, Bu Dia. Okay, so I will move to the third group of the process. So I think this is like most of us are common about this process where we use chemical solutions to etch any kind of products, usually metal products. I know that metallurgists use this kind of etching process to do surface treatments on their samples, and even electrical engineers are familiar with this kind of methods when they develop this IC or PCB components. And in general, we have 2 ways to etch materials. We have the wet etching and the dry etching process. In wet etching, we use liquids to etch the substrates. In dry etching, we use gas to etch the substrates. In wet etching, usually the etching process is isotropic. So we have this kind of etching process where the etching goes in the same rate in the X, Y, and Z directions. And in the dry etching process, we have an anisotropic process, which is more controllable. And if we go deeper in the dry etching process, we will have what we call as physical bombardment. We have an ion milling, we have a plasma sputtering, we have reactive ion etching, we have deep reaction ion etching, where we combine gas, an ionized gas, to etch our substrates. So we can have this kind of features. So you can see that it's just like a micrometers scales, but it can go deep as like a 10 to 1, or even like maybe 3 to 1 ratio of width and height. So this kind of etching can be used to develop micro products. And the last category of microfabrications deals more on how can we add or we can deposit another materials on top of our substrates. We can use what we call as micro contact printing, or we are also familiar with the vapor depositions process or sputtering. Either it's physical vapor depositions or chemical vapor depositions or atomic layer depositions. Basically, in micro contact printing, we can use the PDMS acting as like a sponge, and then so we can put the PDMS on a chemical substance, and then we can then transfer the chemical substance into another substrates in specific patterns, or we can just use this chemical or physical vapor depositions, which I believe that all of us already familiar with the gas with the something like a gold sputtering process during SEM for the SEM sample preparations. So one thing that I would like to also discuss about this microfabrication process is that we cannot just do this microfabrication process in just in a conventional open air room lab, but we usually develop this kind of technology in this special facility called the clean room facility. So this is the space that I'm here usually working in. We have this clean room facility. We have these yellowish lights to reduce the UV lights contaminations. We have to wear this kind of coveralls to reduce the contaminations due to dust or particles. And if we are talking about the clean room, we have several classes of clean rooms facility, and they are divided by the amount of particles that can go inside the clean room facility. So, for example, it's like I usually work in this class 100 facility. So in the class 100 facility, there should be less than this amount of particles inside the room. So in the clean room facility, we have this closed circulation of air with a HEPA filter that is filtering the air, so we can have a clean air free from dust or particles. Okay, so now I will move to the examples of products from the microfabrication. So for now, for examples, I think we're already familiar with this kind of products. In electronics, we can see how processors or storage are evolving time over time. Like for now, like I think in most of our laptop right now, we can find something what we call as an SSD. And if maybe one of you here are already familiar with this kind of electronics, maybe are into computer stuff, we are familiar with this kind of new solid state drive. So in here, like we have this small NVMe M2 SSD, which is can store like 1 terabyte of memories, compared to this older version of SSD, which is like this size, but it can only store like just almost one tenth of this smaller solid state drive, and it's due to how we can produce a smaller and smaller electronic components inside these storage devices due to our capability to fabricate this device. And even Samsung in their latest presentations told that they can generate this kind of new storage device as small as this size, but it can store like 512 gigabytes. So yeah, we can predict the future will be more and more sophisticated. And we can also see how the microfabrications can produce these things called digital micro mirror device, or DMD. And actually, even we realize or not, this DMD device are already around us. So if maybe you have experience working with this resin-based 3D printer, so this kind of printer works based on this digital micro mirror device. And even if maybe any of you go to watch movies at the XXE, 21, or CGV, and then maybe a large cinema in around the countries. So they actually, for now, using this kind of projectors, and they usually have this kind of logo in the device, the DLP test instruments, which use this kind of digital micro mirror device inside this projector. So realize or not, this kind of device already all around us, and we can also see how maybe some of you wear these things, this called a smartwatch, and we can see how this smartwatch can have a lot of functions. It's so watch are not just to show times right now, so we can see how watch can also track the GPS, monitor your heart rate, and then have this kind of like a sleep monitor, like have a Bluetooth connections to the cell phones, and all of the such technologies can be
2 minutes left.
realized
I'm sorry.
because sorry.
Sorry, you only have 2 minutes left.
Okay. Yep. It will be just a short presentation after this. So this is because we have capacity to build a lot of sensors inside this just a small space of size inside the smartwatch. And also maybe a lot of us already familiar with this kind of blood test. Yeah. We can have our blood sugar, cholesterol, and uric acid in our blood tested just using a prick amount of blood from our fingers, and this is due to this technology called microfluidics or biosensors technology. And in the future, we are expecting that maybe we can have a malaria, a dengue, COVID detection in just in the small amount of device using this kind of technology. And then we can also try to generate this energy harvest energy. We can try to harvest energy using this kind of small piezo microsystems. For example, using this kind of systems, we can try to generate energy maybe from our footsteps, and even we can try to implant these piezoelectric sensors into this bone implants, so we can then have like as biosensors embedded in our body that is powered by using our own movement. Okay, and the way we can observe or analyze the products in microfabrications, if we can use optical microscopes, we can use the contact or optical profilometer, we can use SEM or STM or AFM, which is already exists in the office of the Research Center of Meteorology, the AFM. Okay, so and then it's just for the last section of my presentation. So I just want to update. So where are we currently right now about this micro fabrication technology? So in Australia, we have some things called the Australian National Fabrication Facility, which is exists around the countries. I usually work in this Melbourne Center for Random Fabrications, where we have the capacity to do a lot of process in terms of the microfabrications technology. And back in Indonesia, before I go to here, I have several experience developing this, working with colleagues from the University of Indonesia, developing some micro products using micro millings. We try to develop this micro mixer. So this is micro channels on aluminum substrates, and then we also try to develop this copper micro heater, and then we also try to use this microfluidic channels using micro milling molds, and then we also try to develop this PDMS-based micro pump. As you can see, this is just as large as just a coins. And using this kind of systems, we can try to deliver fluids into the microfluidic chip. And we also try to develop this carbon-based biosensors integrated with microfluidic chip to detect glutamates and dopamines from biological samples. Okay, and actually we can also try to get these micro products using a low-cost methods using these UV lights, and then we can also try to use just some screen printing that is usually used as a like to print something on clothes, and then we can also try to use a laser engraving for acrylics, or even maybe resin-based printer like this. And I just want to show you that there are a couple things happening already in Indonesia that show us going toward this industry. So I try to see, try to look on the news that on May 2023, for example, like in ITB, there were this FGD about the semiconductor industry in Indonesia, and then the Ministry of Industry around at the end of 2022 had this dialogues about how can we have this semiconductor industry in Indonesia, and then also they also have even in September 2023, which is like just last month, the industrial minister have this FGD on how can we develop silica into wafer silicons in order to have this kind of independence on semiconductor industry. And if we try to Google up what kind of semiconductor industry in Indonesia right now, we might come up with these two companies, the PCBA Semiconductor and this Infineon Technologies, which are located in Batam. But yeah, I'm not sure like how far they go with the capacity to produce micro products. So this is just for the summary of my talks today. So we already talked about the historical perspective of miniaturizations, the methods and materials in microfabrications, and then microsystem as products of microfabrications, and how this current condition of microfabrication in and around Indonesia in academic and in industrial environment. Okay, that's the end of my presentation. Thank you so much for the time and place. So I will give the time back to Budia as moderator. Thank you.
Thank you so much, Pak Satrio Utomo. Okay, we will continue to the second session. Miss Talita Asmaria, she will talk about metal aneurysm clip. At first, I will give some short information about her biography. Okay, Miss Talita Asmaria has completed her bachelor degree in University of Erlangen, and then she continued her master degree in University of Bristol. Both are from biomedical engineering, and currently she's working as a young researcher at a research center for metallurgy. Miss Talita has published some journals in these recent years, from imaging data to cranioplasty implant design, Journal of Electronics of Medical Engineering and Medical Information in 2023, and also computed tomography image analysis for Indonesian total hip arthroplasty design at 2022. She also published in some proceeding in conference, and also she made a patent In Indonesia, implan clavicula dengan permukaan tulang torus, permukaan luar torus, kemudian klip aneurisma, dan juga alat ukur gaya tarik pada klip aneurisma. Okay, Ms. Talita Astaria, the time is yours, please.
Thank you, Budia. Hold on, I would like to share screen. Okay. Is it clear?
It's clear enough. Maybe you can make it big.
Okay, is it clear?
Yes.
Can you hear my voice, Budia?
Yes, clear enough, Ms. Talita.
Okay, so thank you, everyone. First of all, I would like to say thank you to the host today, Budia, and all staff and researchers at the Research Center for Metallurgy, Indonesia, for having me and give me opportunity to speak in this colloquium. So today I would like to share to you about my latest research for aneurysms in the brain. So before of it, I would like to give a short explanation first about what is the aneurysm itself, particularly in the brain. So if you look at the picture in front of you, here is the anatomy of our brain, human brain, which consists of several parts of the brain. So inside of the brain, and also maybe the whole of our body, it is certainly contains of vessels. This vessel consists of cerebellum, could be carotid, and also venous. So brain aneurysms is actually, if you look at the picture here, is a cerebral aneurysm, or also called it as the intracranial aneurysm. This is a balloon or ballooning in the blood vessels inside of the brain. So an aneurysm, if we look at clearly, if the neurosurgeon do craniectomy atau bedah terbuka bagian otak, it looks like berry hanging on the stem. So the brain aneurysm could rupture because maybe untreated. So the unruptured brain aneurysm will occur in the space. I will use annotate. Okay. So the brain aneurysm will could rupture, and the effect of this rupture can make further effects called as hemorrhagic stroke, or also called as arachnoid hemorrhage stroke. The number of hemorrhagic stroke in Indonesia as well as in the world also high, and this is one of the biggest burden for our national insurance, or called as BPJS. So that's why this is the main reasons why we are researchers in the Research Center for Metallurgy at the brain try to develop the medical tools for treating the brain aneurysm. Okay, so we would like to move on at the aneurysm clip itself. So this is a medical devices that used in many neurosurgery procedure to treat the cerebral aneurysms. So this clip actually, the clips in front of you, typically made from biocompatible metals such as titanium or titanium alloys, stainless steels, and also cobalt chromium alloy. So they are actually designed in many shapes and also many sizes, and to be placed around the neck. So the neck of the cerebral aneurysm also might be different from each case. This is to prevent for any rupturing, any ruptures, or also leakage. So after it is applied to the neck of the aneurysm, we as the patients, or maybe for the neurosurgeon, hope that the aneurysm will collapse. So back to the main purpose of the aneurysm clips is actually to secure the blood inside of the balloon of aneurysms, to isolate the aneurysm from the normal blood flow, and to reduce the risk of the rupture itself. So the placement of the aneurysm clips will be different to each case, depending on where is the aneurysm happens in the vessels of the brain, because we have maybe 1,000 or 100 branches of the vessels in the brain. So of course, the placement will be different. So the neurosurgeon will be carefully select and positioning the appropriate clip during the surgery procedure to ensure proper closure of the aneurysm neck without obstructing the nearby blood vessels. So that's why the size and the shape of the aneurysms today are has many shapes and size for allowing any type and shape of the aneurysm, brain aneurysm itself, and also the place of the aneurysms. Maybe the aneurysm in the like right brain of the right vessel of the brain may be more complicated than the left, and etc. So here is several types of aneurysms. Like I mentioned before, it comes in various shape and size to accommodate different aneurysm characteristics and also its locations. Some of the aneurysm clips could be straight here and could be like curved clips, and also could be fenestrated. So for the fenestration itself, it could be like just have one fenestration, or maybe say two fenestration as well. And the blade of the tip here is the blade called as the blade of aneurysm clip, could be straight and also could be curved as well. So it is depending on what aneurysm brains that actually happen inside of the brain patients. So until today, the material used for the aneurysm clips also has many materials as well. I will explain it to you about the historical aneurysm clips as well. So they are typically made from, this is the main requirement for aneurysm clips. It should be non-magnetic, corrosion-resistant metals such as titanium alloy, stainless steel, and also cobalt chromium. The material also should be has a biocompatibility factor, and also has long-term durability. So here is the example of the aneurysm clips by a commercial brand of Yarsarpil. Mostly Yarsarpil has produced titanium rather than other materials. Here is the old version of the aneurysm clip made from stainless steel. This is from a brand of German USA. And this also old type of the aneurysm clips made from CuCrMO or cobalt chromium molybdenum alloy, with their excellent properties specified by ASTM F105A. This is to prevent damage and ease the handling itself. So if you look at here, there is no a complicated handling in the edge of the clip. So this clip is actually embedded in a heat-resistant silicone sponge, and also packed in a fully autoclavable metal case, which is very sterile before the neurosurgeon use it. Okay, then another factor that we need to consider in the aneurysm clip, particularly for the manufacturer, is its factor of MRI compatibility. So what is the MRI compatibility itself? Actually, if you look at the picture in front of you, this is the image of MRI scans of old women that already have on an aneurysm clip that implanted for about 15 years. So the woman would like to have MRI examination. Before it, the examiner called the neurosurgeon who placed the clip, and the neurosurgeon confirmed that it was Yasargil clip. So as maybe all people know that Yasargil clip must be MR compatible. It be until 2-3 Tesla. So after that, the MRI was scheduled and the patient reached a point about 4 feet for the bore of the 1.5 Tesla magnet. And suddenly she complained a severe headache. So after this, she was transferred into the emergency room because she has a massive intracranial hemorrhage. And the autopsy of this woman in the tear of arterial wall was found at the site of the clip placement with a fresh blood. So after that, they do inspection of the clip itself. Then it is not Yasargil, but rather than a Kottmann-Sun Q-Sparry angle clip, which is non-very ferromagnetic and contradicted for the MRI. So currently, actually, all modern aneurysm clips are composed of titanium alloys, MP39 and MP359 or nickel cobalt chromium, and also alkyloid or phenox or cobalt nickel iron. Most of them should be non or at most minimally ferromagnetic properties. That's why if if people use the cerebral aneurysm clips implanted, it could be until 25 years and should be compatible at least to 3.0 Tesla. So here is several list of MR unsafe aneurysm clips. So remember that if the Yasargil has campaigned their clips that they are MR compatible, but they also have clips that is not in purpose for permanent clip. Like for example, the neurosurgeon tried to do clipping in the aneurysms, and after several years, they could be taken again because maybe the clip, the aneurysm has already shrinkage, so they don't need the clip anymore. So all Yasargil with the FD of models, with the type of FD in the clip, they are not and they are not safe for the MR examinations. So I try to look at what is the FD. It consists of titanium plus phenols. So another factor about aneurysm clips is the long-term effects, because once the an aneurysm is clipped, means that the blood here is radiated and the aneurysm will be isolated. So there are many studies that try to report the long-term effects of the aneurysm clips, maybe after 10, 15, or 20 years. Hopefully, the aneurysm itself may shrink or become completely occluded. So, if it is occluded, then the clip it could be removed, depending on the purpose of it. So, several studies also reported people who undergone aneurysm clips has more memory loss and cognitive disability rather than another treatment called endovascular quilling, especially in patients with over 50. So that's why after cranioectomy, which the main surgery is aneurysm clipping, there will be rehabilitation after this, such as they do physical therapy, occupational therapy, speech therapy, swallow therapy, and also physiological counseling. So I would like to move to the historical invention of the aneurysm clips. If we look at the early techniques, how actually old neurosurgeons tried to treat the cerebral aneurysms. At the early 19th century, this surgical treatment for cerebral aneurysm was very limited. So mostly they only perform direct ligations, which involve tying off the aneurysm neck with sutures. just I don't know the material of the shutters at the early 19th century. Itu kayak benang jahit. So, however, this method had limitations and carried a higher risk implications, maybe because it is not strong enough. So after that, at the around 1930s, the first clips were introduced as the alternative of direct ligations. Here, these early clips were typically made of silver or other malleable metals and could manually bend to fit around the neck of aneurysms. So they provide a more secure closure and reduce the risk of damaging surrounding blood vessel. So at the first generation of aneurysm clip by Halbert Oliver it was not self-closing. So the first aneurysm clip that could have a self-closing configuration introduced by Frank Mayfield. So here is another further development of the aneurysm clips by Charles Drake, or we call it as Drake aneurysm clips between 1920 to 1998. Here is the clip which he firstly introduced any fenestrated type of the aneurysm. So after that, there is a William Pitlock aneurysm clips, or we call it as long aneurysm clips. They also provide the clips with many different sizes and try to modify the edge of the clips here. Okay. After that, there is also William Pechler Scoville aneurysm clip between 1906 to 1984, which they also firstly introduced about what is called about I don't know how to call it, but this is the first time they used the wire and then try to make it like a pier. And after that, it is developed again by Joseph McFadden. It is still used until today. And then we also have Milton the Hefes aneurysm clips. They are using stainless steel, as I remember. So the development of aneurysm clip has then evolved over time to improve their effectiveness and safety to treating the cerebral aneurysms. Then if you back to the first aneurysm clips that were simple design and required manual bending to fit in the aneurysm. So Hefes after that also developed for its installation tools that could be stick for the edge of the aneurysm clip itself. So after that, we have Thorax Maurice Son Jr. in 1930 to 1992 with this type of aneurysm clips. And over the time, so the design and the materials of the aneurysm clip evolved at the around 1960s. There's introduction of titanium clips that brought a significant advancement, particularly from the Yasargil and Sugita. So titanium alloy offered improved biocompatibility, strength, radio opacity, and make it easier to visualize the clip during the follow-up imaging, such as MRI examination. So here is the founder of Mahmoud Ghazizar aneurysm clip. They developed in 1925 to present. So based on the report, Yasaki aneurysm clip is the most aneurysm clip that used in the world. And second, the most is the Sugita. And Indonesia, we also use these two types of the two brands of these clips as well. There's also Kenichiro Sugita from 1932 to present as well. And in 1960s, as I mentioned before, so the titanium alloys revolutionized aneurysm clip design. So it offered improved biocompatibility, strength, and also radio capacity. They were also easier to handle and to manipulate during their surgery. So here is another modern aneurysm clip by Robert Spector aneurysm clips from 1944 to present. So overall, the modern clip technology that available today in the world is Jasarkir by Sculler, Sugita by Mijuho, and also Spector. I don't know what company that as the production itself. Okay, then we are still talking about the modern clip technology or its development. So in recent decades, the aneurysm clip technology has continued to advance. As you may know that the shape, the size, the material, the configurations, etc., will be developed more and more. So the closer mechanism also, they do examination of it, and they do development to accommodate various types of aneurysm characteristics and also its locations. So based on the figure in front of you, this is from Jasarkir, that Jasarkir has many types of the aneurysm clips, size and shapes. And based on the characteristic of the aneurysm itself, we have many types. For example, we have globus, pier, peak, pilobar, multilobar, and fusiform. And also, since the aneurysm clip is placed in the neck of the aneurysms, means that in fact, the neck of the aneurysm also has many size. For example, like the leg of it may be short or maybe not really short, which is it is applicable for the aneurysm to be placed as our. So here also the aneurysm clip, if you see here, there is a small one and the medium one and the curved and also the fenestrator and also the longer plate of the aneurysms and etc. So besides doing aneurysm clip, we also have other alternatives today, which is developed and starting from 1990s as the endovascular alternatives such as coil embolizations emerged as the alternative treatment for several types of aneurysms. As I mentioned to you before, that the type of the characteristic of the aneurysm is many range. Like maybe they could have enough length for neurosurgeon to put the aneurysm in, but or they have a very short length, or maybe they have no length, even they have no length. So this is the alternative. They could make a endovascular alternative by coil embolization. So just imagine that this is the blood vessel inside the brain, and they do microcatheter. If you ever heard about the stent technology, is actually similar with the coil embolizations in the aneurysm brain. As far as I read from the journals, the mostly used material for the coil embolization is the NETI or nitinol. So yeah, here is the procedure of it. So we have the microcatheter inside to put to the inside of the aneurysm, and then after that it will like show up with the maybe very tiny wire to fulfill the whole of aneurysms in here, and then microcatheter will be withdrawn. So the coiled wire will be stay at the aneurysm filament. Here is the non-invasive technique. So in recent years, there has been a shift towards non-invasive techniques for treating the aneurysm, such as endovascular coiling. This will involve a catheter into the blood vessel and then placing coils to promote the clotting within the aneurysms. However, until today, the aneurysm clipping remains a viable treatment option for certain cases. Okay, then
Sorry, Ms. Talita, kindly remind you about the time.
Yeah. How many time left?
Only 5 minutes left.
Okay. So here are the results about the aneurysm clips. So first of all, many researchers try to look at the clip selection and techniques. They try to investigate various factors that could influence the clip selection, such as the aneurysm size, shape, location, and also patient-specific characteristics. For example, if you see the figure in front of you, there is a secular aneurysm and fusiform aneurysm. Means they will have different treatment and different treatment for the selection of the clip itself. So, yeah. So here is the researcher trying to do many clipping. They could like just only clip at the neck of the aneurysms, but maybe they could do like a many clips instead of clipping the aneurysm with many clips, and also they may have multi clips, like they do mix clips as well. Okay, then if we talk about the reasons about aneurysm clips, we could take a look about the development. It is also still related to the research and development. So at 1968, this is the first generation of the aneurysm clip made from implant steel and has a half spring coil and no jaw guidance. After that, in 1970, it had 1.5 spring coil here and safety ring. Here is safety ring to enhance the closing force and stability. So in 1983, Yasaki makes a final aneurysm clips. This is a patented box lock that could improve the character of the scissoring effects. And after that, in 1995, they introduced with titanium aneurysm clips. So if we look at here, there is also XS clip applier to meet the demand of the keyhole surgery, because sometimes the area or the space during the neurosurgery is very limited. So they try to develop the applier or installation tool as well. So in 2006, they tried to develop the T-bar clip here. This is to expand the any treatment possibilities. And then in 2013, they introduced first mini clips with the fenestration law. If we talk about fenestration, here is clip fenestration. And it also allows to even precise construction of the vascular structure along in the narrow space. Okay, if we take a look in the Yasaki development, they actually made it from the long wire, which already modified at the tip of it or on the middle of it, and they do manually to bend it into the clip, and they do any any metallurgy any metal machinings maybe for placing the wire at the top of it. So overall, we are going to propose if we have brain aneurysms and the neurosurgeon try to clipping it, we hope that the aneurysm will shrivel up due to many reasons. For example, ischemia as well. So once the aneurysm already shrinkage, the aneurysm could be taken or removed. So if we talk about the clip stability and long-term result, for example, many researchers also focus on evaluating the durability of the clip closure, assessing the risk of clip migration or reopening, monitoring long-term outcomes in a patient and clip treatment. So, for example, I copied a study of long-term result aneurysm clip. They state that the complete aneurysm closure with neck demand or report warning confirmed in 127 or 96 of whole data. So overall, from all of that, there were only 18% from the whole data or around 50% patient who needed further management of clipping, but the rest of it are normal. So if we talk about the clip-related complications, they are associated with the aneurysm clips, including clip slippage, clip-induced stenosis, or narrowing of blood vessels, and also clip-related ischemia, which reduce the blood flow. So many researchers aim to identify risk factor and develop many preventive strategies and also improve the patient outcome. So if we look at the development by the Yashardil as well, here is the blade of the aneurysm clip, which is at the surface, at the inner surface of the blade itself. They develop the surface to prevent any clip slippage after applying the surgery clipping. So here is the intraoperative picture showing that the clip narrow at the neck of the aneurysm clips and the Doppler probe to identify any stenosis on the aneurysm clips. So many novel clip technology also try to develop, for example, they try to find a new material that may be more suitable for the aneurysm clips, such as has shape memory alloy clips or resorbable clip, which they then have potential to provide improved outcomes or reduce long-term complications. For example, here they try to biodegradable magnesium stent as alternative for clipping. As you may already know, in the vascular coiling, they firstly do inserting the stent before to coiling. So besides of it, there's also development of ceramic aneurysm clips and also zirconia polyurethane aneurysm clips. So as far as I know, this type of materials is actually trying to have a more safety in the MRI examination if they are using metal clips. So that's why the advanced imaging techniques such as high resolution MRI and angiography are being used to assess the clip placement accuracy, to evaluate the clip stability, and monitor the aneurysm healing post-surgery. That's why in our research group, we are trying to also develop to do preliminary study of the properties of PU, MGZN, or polyurethane magnesium and zinc for aneurysm clip applications. So here, as I similar before about the endovascular alternatives based on clipping, we could do coiling and also flow diverter and also stent as well. Yeah. So here is several materials. We'll need like around 5 slides more. It is a titanium aneurysm clip by Michuho Sugita titanium to aneurysm, but Yashar also has this type of material. They are lightweight and strong metal, just mostly used in the medical implants. It has highly biocompatible, well tolerated by the body, and does not cause any adverse reactions, corrosion, etc. So they are well known for their durability, resistant to the corrosion as well. So before titanium, the inventor of aneurysm clips, one of the inventor also developed stainless steel. This is another commonly used material for the aneurysm clips, known for its strength, durability, resistant to corrosions, and often used in cases where a higher clip stiffness is required. If we look back at the history of the aneurysm clips, the stainless steel introduced by the Havettes. This is a pivot type clip made of stainless steels. But in 1977, a study found the possibility of head clip failure due to mechanical factor that must be kept in mind in the post-operative aneurysm patient. So if you look at here is the imaging before, after operations, the intake of the clip is shown in a good positions. But in here, 10 months after post-operatively, the fracture plate is seen in blood widely separated. So it is a quite danger. So another material for the aneurysm clip, also cobalt chromium, that we are in Indonesia mostly use this one as well, because maybe the price is cheaper than titanium. So the COCAR offers excellent strength, corrosion resistance, and also biocompatibility. So they are well known with the high tensile strength and flexibility. So this is the example of cobalt chromium sugita aneurysm clip. They have shown acceptable for the use of MRI system up to 1.5 Tesla in the clinical use. Okay, here is the result for reliability of the cobalt chromium alloy aneurysms created after long-term implantation. They are using, they have been used for 11 years, 17 years, and also 20 years. And overall, they demonstrate that clips retain their mechanical properties with the in vivo test for a long time, which indicates the reliability of this clip. So that's why maybe it is a good choice until today. Here is several types of the cobalt chromium sugita aneurysm clips. Okay, another one is the nitinol. Maybe it is quite different with the brain aneurysm clips, but it is used for the cardiac surgery. So here is the clips. So actually nitinol is a shape memory alloy that was of nickel and titanium. It has a unique property that able to return to its original shape after deformation. So the clip can be compressed for insertion, then expand to the original shape once in its place, providing a secure closure. So in the cardiac surgery, we also have found about deep sternal wound complication or DSWC that have incidence of 28% and could carry a significant mortality or death. So the cardiac surgeon, based on this source, they try to apply the clips to steel wires and apply to the manubrium, and one is near the sigmoid, and they are trying to tighten it. So at the body temperature after they apply it, the clips will break into the original shape and has a factor of rigidity. So this technique of sternal closure is then important for important factor that affecting the incidence of dehiscence and also wound infections. Here is our latest research about reverse engineering of aneurysm clip. We got a sample of sugita aneurysm clip for a neurosurgeon at the Pelita Harapan University or Siloam Hospital at the Karawaci, and then we try to do reverse engineering by scanning it, and after that we do 3D model and try to print it using the SS and also TI or titanium. So for the configuration of the size of it or shape of it, it could be precisely same. But for the closing force or other purpose, they are failing to fulfill it. So this is the hopes of the aneurysm clip development in Indonesia, that until today, plenty companies abroad have successfully fulfilled the need of aneurysm clips portrait. As you may see, this is the ceramic mini aneurysm clips. They have developed the cutting-edge technology that's related to the clips. Then we hope someday we as an Indonesian user could provide this technology where our national capabilities. So that's all about my presentation today. Thank you for listening me.
Thank you so much, Butalitas Maria. Very nice presentation. Okay, let's continue to the next session, question and answering session. Actually, we already have a question here. Oh, please wait. Let me read a question. Okay, the question is for Pak Satrio Utomo from Pak Riona Ihsan Media. The question in Indonesia, and I will say it in Indonesia. Mohon izin, pertanyaan yang diajukan berkaitan dengan miniaturization. Yang pertama, apakah memungkinkan untuk dapat berkolaborasi dalam penelitian seperti matching fund? Kemudian beliau mengatakan ada pengalaman dalam riset in design of macrofluidic channel in terms of concentration of mixing yang sudah dipublikasikan di international conference. Pertanyaan kedua, bagaimana prospek mitra tentang microfluidics device ini, apakah sudah eksis di Indonesia, mengingat di Indonesia sendiri masih impor dari negara tetangga seperti Singapura untuk alat-alat LOC ini. Baik, oke, for Pak Satrio, dipersilakan.
Ya, Budia, terima kasih. Berhubung pertanyaan bahasa Indonesia, berarti jawabannya bahasa Indonesia juga kan? Ya, kepada Bapak Riona Isan, terima kasih atas pertanyaannya, Pak. Terkait matching fund, kebetulan saya juga sempat aktif juga di lingkungan perguruan tinggi, Pak. Jadi, seingat saya sih matching fund mitranya industri ya, Pak ya. Cuma nanti mungkin bisa dipastikan lagi begitu, Pak ya. Maksudnya apakah kolaborasi di matching fund ini konsepnya seperti apa? Kemudian kolaborasi juga ini maksudnya nanti dengan siapa gitu institusinya. Kalau Bapak sendiri kan dari Muhammad Bandung, ini kalau pengalaman saya kalau di Indonesia yang sudah ada kegiatan penelitian histori penelitian di bidang mikrofabrikasi, mikrofluidik itu ada di Fakultas Teknik Universitas Indonesia di Departemen Teknik Mesin, nanti dengan Bapak Yudan Plaza. Nanti kalau mau diarahkan ke grup riset beliau, nanti bisa kita bahas lebih lanjut. Kalau kemudian memang mau diarahkan dengan institusi saya tempat saya belajar sekarang di Universitas Melbourne juga ya, itu berarti kan nanti lintas negara juga aja nanti bisa dibahas juga agar detailnya mau seperti apa yang dimaksud kolaborasi. Cuma konsepnya sih ya sangat terbuka begitu ya Pak ya dengan kolaborasi. Kemudian yang kedua tentang prospek mitra juga ini kalau bicara mengenai industrinya microfluidics ini sepertinya sih kalau yang benar-benar bisa memproduksi begitu saya sih belum ketemu begitu Pak ya. Saya tidak tahu kalau kemudian mungkin kata sudah ada yang mencoba mengembangkan. Sehingga biasanya sih rata-rata kalau kita bicara mengenai microfluidics ini masih di lingkungan perguruan tinggi, biasanya teman-teman dari ilmu kesehatan, ilmu kedokteran itu yang memiliki interest begitu menjadi user dari alat-alat microfluidics, dan nanti teman-teman dari engineering yang coba mengembangkan, dan itu pun juga masih menggunakan konsep rapid prototyping gitu ya Pak ya, jadi masih belum menggunakan konsep mass fabrication. Jadi kalau di UI sendiri misalnya pengalaman saya ya mungkin menggunakan micromilling, menggunakan litografi gitu, nanti dibuat alat microfluidics-nya dan nanti kemudian diujikan di teman-teman di kedokteran gitu. Dan kalau bicara mengenai kualitas device-nya pun juga ya antara microfluidics device yang sudah menjadi komersial begitu dengan yang diproduksi di lingkungan perguruan tinggi pun juga sebenarnya juga skalanya ya masih belum comparable seperti itu sebenarnya. Gitu. Cuma ya rata-rata memang sekarang produk microfluidics pun juga sudah banyak yang dikomersialkan, maksudnya bisa diadakan gitu ya, kita bisa beli misalkan dari Jerman, dari Taiwan, Cina pun juga sudah ada yang bisa masuk ke Indonesia produknya, dari UK, dari Prancis gitu, dari Swiss juga ada. Jadi rata-rata mungkin kita masih impor seperti itu.
Oke.
Ya,
terima kasih. Iya, terima kasih Pak Satrio. Ini kebetulan apa ada tanggapan dari Pak Rionanya? Nggak ada ya sepertinya. Oke. Kalau begitu kita lanjut. Barangkali ada pertanyaan selanjutnya? Is there any question? Okay, then let me summarize first. Okay, so from Pak Satrio talk, we can see that microfabrication currently is being studied in every area of human life, and then things are getting smaller but more powerful, and for the microfluidics also has been studied in and the University of Indonesia. But how about the semiconductor industry beside the one you showed from in the Batam? Has also it's been commercialized, or is there any factory in Indonesia who produce semiconductor devices?
Yeah, so I personally do not have any direct experience, direct contact with the industry. So I just Google, try to look something, because I think it's kind of strange for a country like Indonesia. It's a large country. We know that we already try to develop this industry 4.0 in our country in a massive scalable way. We have a lot of startup companies. We try to implement AI, ML, IoT technology in Indonesia, but then it seems that we don't have any semiconductor industry in Indonesia, which is kind of strange, because it's like we built something, but we don't have a strong foundation. But that's what I get from the Google. So we have like that two industry, and they're basically also like just a foreign company which invest in Indonesia. So it still, I couldn't say that is an Indonesian owned company. It's just like a foreign company putting its line of production in Indonesia. So it's just that's all. So still there are a lot of homework that we need to develop considering the semiconductor industry. That's what I have in mind. Thank you.
Okay, thank you, Pak Sado. Okay, next for the talk from Ms. Talita. Please correct me if I'm wrong, because I haven't learned about aneurysm first. So it's actually because the dilatation on the blood vessel, so to prevent hemorrhage stroke, we can do coiling and also clipping. Is it right? Okay, and so actually for I think it will be more useful for older people, right? And so when we design the aneurysm clips, so how long should we predict the durability of the clip aneurysm? And is there any trick to achieve it?
Actually, the type of aneurysm has a permanent and also a temporary. So maybe for permanent, then after doing clipping, it will be permanently, like implant permanent. So besides that, we have also temporary clipping implant. For example, after the aneurysm is already shrinkage, or maybe just like gone, the aneurysm clip would be removed. So for examination, the durability, we maybe, I don't know, in Indonesia have already done investigation on it or no, but I read some on the journals that they do inspections about long-term or durability effects after using aneurysm clips, like 15 or 20 years after the surgery.
And so if for the permanent, it is placed in the brain.
Yeah, but as far as I talk with the neurosurgeons, in Indonesia, maybe they try to do permanent, because the cost of doing ray surgery, like applying for cranioectomy again and then open, the school again not only takes time but also takes a lot of money. So that's why they applied for they treat it for permanent. But actually, all aneurysms could be taken if the patients want it after they see on the image that the aneurysm is gone.
Oh, thank you so much, Ms. Talita. Okay, is there any question from the audience? Okay, I think no more question. Thank you so much for the speaker. Actually, at the rundown, okay. Since no more question, I would like to ask for the speaker to give their hope and also some closing remarks related to the current status of research in Indonesia and also the prospect to the near future. Okay, please. To Pak Satrio first,
Yeah,
maybe.
Budia, thank you so for the closing remarks. Just like I told before, yeah. So it's quite strange for Indonesia as a large country that has already tried to implement Industry 4.0 in almost any aspect of its activity, but I think we still do not have a strong foundation for the microfabrication, miniaturization industry. We still rely heavily on foreign countries. So I think it will be better if the government and academic and also business society can sit together and then try to develop this industry. We already see the initiations from the Ministry of Industry that I showed you earlier in the news, but I think we still have to work faster and then try to build this industry in Indonesia. And this is a spoiler for the next speaker. Raga, you want to say hi? Spoiler for the next speaker. Thank you, Budi.
Then your voice a bit low. Maybe you can
Yeah, thank you,
say it
Budia.
loud. Okay.
Yeah, that's all. Thank you.
Okay. Thank you, Pak Satrio. Next for Miss Talita. Talita.
Budia, I found a questions in the link of questions.
Oh, okay. Sorry, I haven't read it. Oke. Oh, ada pertanyaan selanjutnya untuk Ibu Talita terkait klip aneurisma, apa sudah melalui tahap uji klinis dan apakah sudah ada NIE?
Ini kayak izin edaran mungkin NIE. Belum, mungkin siapa nggak tahu yang saya tanya. Not yet until today we are still do investigation on how to reverse engineering. Maybe hope someday we could do any commercialization steps or clinical tests for it. Thank you.
Thank you, Bu Talita. Okay, next, since no more question, maybe you can give the closing remarks, your hope and the future prospect of this metal aneurysm clip in Indonesia.
For the manufacturing of the aneurysm in Indonesia, maybe it's still far away from our current development in, but with do step-by-step improvement or Indonesia support the aneurysm clips, maybe we hope someday that we could do we could provide the aneurysm clip in Indonesia by our own manufacturer agents. So thank you.
Thank you so much, Ibu Talita. we can see that from this talk that we have a lot of work to do to develop our country. And then thank you for the audience for coming to this event. And before I really end this colloquium, I will promote our next colloquium series. Wait. For the next colloquium, we'll have we will have the next colloquium next Friday. The topic will be sustainable engineering and innovation in ferronickel slag and metalloid alloy. The speaker will be Agaridova, the one in the Mr. Satria Utomo slides. And then the second speaker, and the topic, development of carrier selective interfacial film for photovoltaic. And then the second speaker will be Miss Annie Febriana. The topic will be ferronickel slag, potency and processing challenge. And the moderator will be Miss Latifa Hanum Lalasari. Please save the date. Don't forget to meet us again in the next colloquium. Okay. Thank you so much for your attention. Thank you for the speakers. Thank you also for the staff. I think it's time to close the colloquium. Okay. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh. See you later.